Awesome. So hi, I'm Steven Gonzales. I am from San Antonio, Texas, and I work for VirtuStream. Some of you might have seen on the intro side, my name is EMC Cloud Services. That is because VirtuStream is now a member of the EMC Federation. So not too long ago, EMC acquired VirtuStream, and VirtuStream is now officially the Cloud Services business arm of EMC. So VirtuStream takes all the things that you would normally meter by the drip and has bundled them under the VirtuStream brand. And thinking of EMC, you traditionally think of like people that ship storage appliances to your data center, right, and manage more of the storage aspect. So VirtuStream in general provides IaaS, infrastructure as a service, object storage, and managed services. And we're primarily known for running mission-critical enterprise workloads in the cloud. So we take things like big Oracle databases or big, nasty, hairy SAP deployments that companies rely on as the lifeblood of their infrastructure, and we take those and run them in a cloud computing environment. So I work under a particular unit that is part of a larger product offering called the VirtuStream Storage Cloud. So the VirtuStream Storage Cloud is an S3-like object storage interface. We have about 2 exabytes of storage deployed in about 25 data centers around the world. So my team, I work on a team called Platform Engineering. So we're a smaller subset that supports that storage cloud. My team is primarily responsible for running the compute platforms that power some of the services that run in front of the object store. So my team is responsible for running an OpenStack distribution across 8 data centers right now, and an Apache Mesos platform that runs in 8 data centers as well. My team is also currently responsible for providing Kafka clusters as a service, and Cassandra that we use for a lot of the metadata store. It kind of supports some of the stuff within the object store. So let me kind of explain a little bit of the applications that I'm going to talk about, and kind of go into detail of an application that we use to help deliver the object storage platform, some of the problems that we had coding and maintaining and deploying that code, and how that eventually led us to the Mesos platform. So this application layer in front of the object store is absolutely mission critical to performance of the storage system, right? That's the endpoint that the customers hit and that the customers push all their data through. It handles all the object ingest that comes into the platform. It also provides a nice layer for us to capture metadata and other services before we send it back to the component of the object store that actually takes the file and puts it on the disk. It has really high throughput network I/O requirements. Some of these containers process up to 6 gigabits per second of traffic, SSL terminated, so they're using CPU and a lot of network I/O. Another unique challenge that we face when trying to run this is that we're dealing with long-lived connections. So we might have connections coming in from storage appliances that EMC has in people's data centers that then offload data to the object storage cloud and might transfer that data over slowly. We're also taking in a lot of connections from mobile devices as well, right? So when you think of mobile device connections, uploading a photo in the background, right, takes a really long time. And so we have, really long-lived, slow upload connections that sometimes upload some pretty decent file sizes. And that presents quite a bit of challenge when trying to orchestrate your application. So starting out, the application that powered this ingest was a really big monolithic app. It had a few supporting services that would run on the same hosts. We deployed these in virtual machines, on a lot of virtual machines. And we would deploy big changes all at once, right? So we would be on a longer release cycle. So think of like working on some new features for a period of 2 or 3 months, and then trying to push those changes out at massive scale across production, right? For the most of the part, we would install new packages on the host, and then help the service to make sure that those long-lived connections stay running. So we had a lot of problems deploying in the VM environment, keeping all the dependencies installed and updated on the host, along with security patches, managing different dependencies between the different services that started to be installed on that host. So, one app depends on some version of Python, and another app depends on some other version of some Python dependency that's shifting, and how do you keep those segregated and keep those in line and test all of those so that you don't break any of the applications. We did a lot of manual testing. So in the beginning, a lot of the application was tested by the developers. They would continuously make changes to their code, and then once they got to a point they felt ready to test, they would try to get it set up and manually test a bunch of the commands that would run against the interface. So we also had some really half-baked configuration management. So we just started introducing salt stack into our environment to help manage some of that config on these hosts. This app was particularly complicated to manage configuration, restarting of services, hubbing of services, dependencies on when you could do what on what machine, and that led to not a lot of progress on the config management side. So no orchestration, right? We would end up like figuring out what the series of commands were we needed to do to be able to deploy whatever the next big change was, and then we would go forth and deploy that. And so that became really, really, really scary. Right, whenever we had to make a big change into production. And that also led to a lot of the, worked on my machine, right? The developer tested it, worked on his machine, we think we're good to go, start doing the deployment in production, stuff starts going bad, right? It's because we didn't have that consistent environment. That was essentially kind of an example of what our application deployments look like, a bunch of frenzied commands on the keyboard, struggling to roll back changes if they weren't successful. And we also had kind of a more traditional team structure at the time, right? We had an application dev team. They wrote the code, they manually tested the code, they were not on call. So we did have, luckily, a good culture of people that were always there to pitch in and do the work, but it was the operations team that had to deploy the application, and they're the ones that had to keep it running. So when something went wrong and services need to get restarted, the operations team had to handle that. If there's a problem with the service and it's throwing a lot of 500 errors, the operations team is the one that gets paged in the middle of the night. And if they needed help from the developers, they gotta hope that somebody answers their cell phone when they're calling, right? There's no on-call rotation for the developers. So we thought about it, and we thought there has to be a better way to do this, right? Like, software development has moved past this. There's a lot of new methodologies and design paradigms. There has to be a better way for us to get through this problem. And so we started taking a look at the concepts of continuous delivery and what that meant. Keeping your app in a deployable state at all times, right? So every single commit that you make that gets merged back into master has to keep the application in a working state. No big refactors in the sky, right? Where you go up and mangle some piece of code for 2 months where it's not in a working state until it's time to bring it all back together and get it deployed, right? That had to stop. Every single commit had to continue to keep that app working. So what does that mean? That also means you need a way to validate if that app is working after every single commit. So we needed to be able to start writing automated testing, have some continuous integration that we could run, provide a build system, right? Write the automated tests that we could run against those services. We also wanted to get in the habit of deploying small changes really frequently instead of those super monolithic releases. And having to find a way to have a fully automated deployment that's consistent every time. So why do you want to do these things, right? It helps you deliver features to customers faster. We are running a cloud service, so it's not like we're adding features and then waiting to ship that in our next version to a customer. Customers are consuming our service live 24/7. So the faster we deploy features into production, the faster customers can use them. Automated testing is obviously way better than any of the manual testing you could do, and it's consistent and repeatable. And we felt it's way less risky to deploy a really tiny change into production every day than it is to deploy a whole bunch of changes all at once, right? If you deploy one tiny change to an API and you start getting errors, guess what? It's really easy to identify what the problem is, right? It was your last little change. You don't have to go pick through the last 400 commits to figure out which is the one that broke my product. The sooner you find the problem in the app, the easier it is to fix, right? And getting to that automated deployment state was going to make that a lot easier. So we also started exploring, so what is this microservices hubbub that everybody's talking about, right? And so how does that enable making continuous delivery possible, right? So making many small applications that communicate instead of the giant monolithic app, so you can help isolate your changes to smaller services. keeps the applications easier to understand and modify, right? It's kind of like when you think about the programming paradigm of like naming your function correctly, right? If you can't give your programming method a name, then it's doing too much, right? Same with an application. Once you can't describe what that application is doing, it's doing too much, right? And it's time to break it apart. That made continuous deployment of the application a lot easier because you're just working on deploying smaller components whenever they have individual changes. And it also really helped us scale, right? We have a ton of widgets going in. Different components of the system are under different load at different times, right? So you want to be able to, like before we would scale out the monolithic app, oh, it's getting busy, we need more instances of it, right? But in reality, only certain components of the app are the bottleneck. So now we can scale out those components individually, right? And make those grow larger. So we also wanted to be able to take advantage of new programming languages and frameworks. We had a lot of Python before, a little bit of Lua. Now we've got to branch out and do some cool stuff with Golang and concurrency, and kind of be able to find the best tool to do the job, right? Or if we find some superstar hotshot programmer and he really loves some functional programming languages and he can change our world with that, he can implement his microservice in that without necessarily like destroying all the rest of the application. So we thought, okay, so that's what we want to do. How do we get there, right? What's our first step? So we thought we'd try out Docker, right? Totally solved all our problems and a presentation. Thank you. No. So, you know, Docker did have some really good advantages for us. It really did help us along this journey, right? But everybody knows it doesn't solve all your problems. It did let us bundle the application right into a Docker image so that it's just a single artifact that gets deployed. All the dependencies package into that artifact. Isolation between all the other microservices. No longer have to worry about those conflicting dependencies. Installing a bunch of frameworks on each of the hosts, right, and any compatibilities between them. That made it really a lot easier to break up the monolithic app that we had. It's really easy to spin up containers for testing. It actually really enabled kind of a renaissance that we had on our automated test writing, because now using little tools like DrCompose, you can spin up a small working stack on a developer workstation and execute your test suite against it. We made it a really big priority once we had that going to start beefing up the test suite and spending a considerable amount of time doing so. And that was also easy to transfer that same test suite that can now run on a developer machine to also run on a build environment. Right? And it made it a lot easier to scale instances across the whole thing. So we also realized that you still have to configure your containers. You know, I listened to a pretty good talk earlier on Mesos, where they were talking about going to environmental variables. We tried a different approach first. We tried actually having to mount the file system and read configuration files, and we used SaltStack to run and manage the application, the configuration of those containers. So we would use Salt to lay down stuff on the operating system. We already use Salt to manage the host OS and things like SSH, and syslog, and NTP, and users, and all that kind of stuff. So we added in a formula for managing the Docker installation, keeping that up to date. And then we started writing different salt formulas for launching the specific containers, right? That was pretty useful and helped us at least keep the deployment of the containers automated and still be able to view that stuff in Git. And it did make changes a lot less scary, but it didn't solve all of our problems, right? This still was somewhat of a tangled mess to manage. When you're managing those configuration files, you're still writing config code for each new service, right? So having to manage those config files on each host, you have to know a couple of things. Yeah, A, you have to write salt to make a template for that config file that has to go. You have to drop it in the directory in a way that you could have multiple instances of the app running with different configuration and be able to manage that on the host. You have to keep track of what runs on the host because you have to apply the right salt state to it. You also have to keep track of what runs on a host because if your host fails, you need to know where you can, what services were running on there and where you can recover them to, right? You also have to keep track of ports. So when we were doing this, you know, Docker networking to simplify how it really works, it's really sharing the interface of the host and getting some port, you know, that's dynamically mapped and that you specify on the host. You have to track what ports the Docker containers are exposing externally on that interface, and that you don't have any conflicts among any of your services, right? So that's still much of a hassle to kind of track. When a service fails, you still might have to recover it, right? Docker restarting it might not be the right answer. Changes still have to be really, really, really carefully orchestrated. Think about linked containers, right? If there's dependencies on those, you upgrade one, you have to restart the other, right, to maintain that link. So that ended up with deployments, while being more automated, were still a series of commands that an operations engineer had to run. Ah, yes. The ever thorn in my side. What about those long-lived connections? The promise of immutable containers that Docker brings does not work for long-lived connections very well, at least not in the method that we first tried. Right? Restarting a container to upgrade it, what does that do? It drops all the connections. Right? So, not very good for a public object storage service if you're severing all of people's uploads every time you do an application deployment. Like I said, some of these containers are processing like 6 gigs per second. I can't really stick a proxy service in front of them, right? And then balance that across 20 containers. And I can't handle the throughput. So made us really sad, and this was like much internal debate around this and long arguments in Slack. We ended up, for some of these containers, having to upgrade the package inside the container and sending a hop signal inside the container, which made us all feel really dirty for a while. So how did our team kind of transform when we moved into this model, right? We were churning out more configuration management code. We were still wanting to churn out more features and develop more microservices, and we still had to operate the platform. So this kind of created a new formation of teams. We had the app dev team, right, still writing their application code, testing their application code. Then we had a separate automation team, which you can think of as like a DevOps team all by itself. We would write the config and deployment automation, and we would only test the configuration automation. We wouldn't necessarily test all the interaction with the app. And then we'd have the operations team, which deployed the application, and again, we're the only ones that got paged when the thing wasn't running, right? So some problem with deployment, hope you can find someone that's doing the automation to come and help you out with that code, right? Problem with the app itself, hope you can get a hold of a dev to help you, get through that situation. So it's still a little bit, it broke up some of the responsibilities, but it still didn't really solve our problem. So we thought, again, there has to be a better way to get through this, right? So we started researching a lot of the different platform services that are out there. We looked at Kubernetes, we looked at Swarm, and we spent a lot of time looking at Apache Mesos. Ultimately, we ended up settling on Apache Mesos for a couple of pretty cool reasons. You can kind of think of Apache Mesos as a distributed kernel or operating system that covers your cluster of compute, right? So it lets you treat all the compute you have in your data center as a single pool of resources, right? So it's aggregating all the information about CPU, RAM, disk, and abstracting that layer away from you as an application developer. It lets you do resource-based scheduling, so you can schedule based on the needs of your application, CPU, RAM, disk, etc. It provides HA, so you can auto-reschedule failing workloads. You tell Mesos that it needs to run 12 instances of a task, it's going to make sure that 12 instances stay running. You can easily scale the number of app instances, right? You want to deploy 7, cool, you hit the API, tell it to deploy 7. You need to up that to 12, hit the API again, now you have 12 instances. It gives you native isolation between tasks using C groups. So you can have limits on RAM, how the CPU is utilized on the machine, how much disk can be consumed by that container. And you have the flexibility to write your own frameworks. So that was a big one for us. We knew with the long-lived connections and high throughput stuff, we were going to have to foray into the world of writing our own frameworks. We also really liked a lot of the work that's going into some of the Kafka frameworks. So we run some frameworks for supporting Zookeeper and Kafka on top of Mesos as well. One thing we really liked about the concept of frameworks is it lets you manage your application orchestration using a real programming language, right? So we deployed Kafka before with configuration management tools, and trying to orchestrate, think about trying to orchestrate a configuration change to something like Kafka. You have to update the configuration on one node, restart the broker. Somehow in there, you have to test that that broker is rejoined and is healthy, and then move on to the next node, move on to the next node, move on to the next node. Well, the Mesos framework helps you do that kind of activity, but it lets you write that logic using a real programming language rather than trying to shoehorn that into a bunch of YAML or DSL language that you would get from your configuration software. So what is a Mesos framework? A framework is basically a scheduler that's allowed to use resources on your pool of compute that's managed by Mesos. So Mesos, bare bones by itself, doesn't do anything. It's the frameworks that make you able to actually launch the tasks and run them, and they're your interface to the underlying Mesos agents. So scheduler executors, like I said, can be written to perform certain type of tasks. So there's some for deploying containers that run a long time. There's some for deploying scheduled jobs. There's some for running Kafka, some for running Zookeeper, Cassandra, Elasticsearch, etc. The framework has two parts. It has a scheduler that registers with the Mesos masters, and that's what receives offers from the master and makes decisions on whether or not it wants to schedule. And it has the executor, which actually launches the tasks on the node. So the master determines how many resources to offer the different frameworks you might be running, and then the frameworks make the decision on whether they want to actually use that offer and then run a task. So I have a quick little diagram to kind of explain how that works. So on the bottom, you'll see the agent one. Step one to this is the agent reports up to the master what resources it has available. It says, hi, I have 16 CPU, 8 gigs of RAM, and half a terabyte of disk, right? The Mesos master then talks up to the different frameworks, and it decides what order to offer the resources to the frameworks to. It has a fair sharing algorithm, so it'll tend to offer resources first to a framework that has less tasks running on it and a framework that's more heavily utilized. So if it offers resources to a framework, it can say, hey, these are the resources I have available right now on this particular agent. Do you want to schedule anything here? The framework can say, oh, well, I have some constraint that says I can't work on the attribute that this resource provides. I'm going to reject the offer and wait for a better one, right? Then it might move to another framework that says, oh, all I care about is that you have 1 CPU and 2 gigs of RAM. I'm ready to go. I'd like to launch some tasks, right? So we'll tell that to the master, which will then use the executor to launch that task on the slave and make sure that that's visualized. So Marathon is a framework specifically for orchestrating containers on top of Mesos. It's what keeps most of our web applications running. It has constraint-based scheduling, so I can assign roles to hosts. I can assign affinity and anti-affinity rules, right? Like, I want to run 12 containers, none of them can run on the same host. Or I want to run 3 containers, they all have to run on the same host. You can assign attributes to the slave, like this slave has SSDs and this slave has spinning disk. So I can tell my container constraints that I require the slave to have an attribute of SSD. Whatever I'm doing requires high disk performance. It lets you now deploy your containers through a REST API. So you can easily scale your apps just by hitting the API and bumping the number of instances. Marathon also offers rolling restarts, which is pretty handy for your more traditional REST API type of application. It'll loop through the container and upgrade to a new version one by one. It allows you to put in health checks, so if it doesn't pass that first health check, it can roll that change back. It's really useful for your basic REST applications. It also has a form of application dependencies. If you're deploying a group of applications together, you can help orchestrate the order that those services get deployed. So just a high-level picture of what our platform kind of looks like internally. We have a bunch of Mesos agents, which right now, for performance reasons, run on a bunch of bare metal compute. And sometime now, we're finding we have some workloads that would be okay in a virtualized environment. We're hoping to kind of expand that out into our OpenStack cloud. We have our Mesos masters, and we run Marathon. We actually converge the Zookeeper nodes, which is what Mesos and Marathon use to keep quorum as to who's the leader. So both of those always have a leader, and then they have standby nodes, and they use Zookeeper to negotiate quorum on that. So in our deployment, we have the concept of Mesos controllers, and on those controller nodes runs a master for Mesos, a master for Marathon, and Zookeeper all in that same place. So users can hit the Marathon API, schedule apps, get scheduled on the agent, and then we get into some of what I'm going to cover in a second, which is how we're doing service discovery. So just an example of a Marathon deployment, super simple, right? You can tell it that you want to run a Docker application. This one's using an image called Python 3, and it's just launching a generic HTTP server, and we're telling it what CPU allocation we want, and then it wants a whole bunch of memory. And you can specify the port mappings. So let's talk about console a little bit. So console is a product by HashiCorp, centrally focused on service discovery and providing key value for configuration management. So you still have to configure your applications. Console offers a key value store to help do that. So we have a kind of a system that we use for namespacing the different key value items inside of console. And we instrument all the containers that we deploy on our platform to read their configuration from console on Spider. So whether that loads and sets environment variables, or whether the application itself reaches out and talks to console, or whether we use some of these popular services like confd, console template, or container button. So if you wanted to write your application to a config file, you can use something like console template, which will read in your configuration from the console server, write it out to a file, and then let you start your application inside the container after that happens. And it'll read that config as part of it. There's other services like Container Buddy by Joint. Those will actually monitor console for changes to configuration and have a method for helping the application inside to reload new configuration changes. And that really all we have to pass when we schedule the application is the address to the console servers itself, which for us is a static DNS entry. So we also use the service discovery components in console. It's really easy for services to register themselves. It's an HTTP API you can call. It lets you discover other services via DNS or via HTTP. When an app fails, it'll auto-update those addresses, right? It'll update the entry in service discovery. It'll update your DNS record. So you really no longer have to worry about where your services are physically running, right? So, before when we were deploying with containers and SaltStack and these services had to talk to each other, I still had to know the address of the host that they were running on, right? And what was running on each host. So we no longer have to worry about that using DNS. Console also has the ability to add custom help checks. So it can check services out of the service registry based on possible failing help checks. So we're actually starting to use that more and more to be able to instrument draining in some of our containers, right? So we can actually write something into the application that tells it to fail the help check and let it drain. So while the Mesos task won't exit, we can take it out of DNS and then other services don't. So how does console work for service discovery? So we have Mesos accepting requests in a super simplified version. We personally read from the Mesos state that keeps a list of all running tasks. There's a couple of different options for integrating service discovery with console on our Mesos platform. There's some that are written specifically just for Marathon to register for console. We had a feeling we were going to be running other frameworks, so we decided to work from the Mesos state.json. So we have another application as a fork of, we started with Mesos console, which was written to pull from state.json and then update console with a description of all the tasks that are running. But we ended up making a fork of Mesos DNS and putting in an abstraction that lets it use the console DNS backend. So when you launch an application in Marathon or entering service, it'll register that entry into console. And then when an individual application or task gets scheduled to run, it'll update, it'll register that task in console and then give it a DNS entry that maps back to the service. So kind of an example of the service discovery here is I will have, say up here, I have my service-b my service-b.service.console as the DNS entry. Just pretend that's a service that needs to discover my service.a, right? So all it has to do is talk to the DNS entry service-a .service.console, and then it uses round-robin DNS to talk to each one of the containers that are registered as being a task related to that service. So it's each, like if, say, this agent one, this task on agent one fails, it will, could get rescheduled on another host. So as it fails, that DNS entry will get removed. It'll get taken out of the round-robin pool, so applications stop talking to that particular host. When it gets rescheduled on another slave, right, it'll get that new IP address and it will get added back into the DNS round-robin for that particular service. So now I no longer have to care about where the services are running. I don't have to take any specific action when the service fails. Not only does Mesos recover it, the address that all the other services are using to talk to it is also updated automatically. I don't have to manage configuration data about where the other services are. I can just talk to them over the expected service DNS address. And no more writing config management code for new services. So again, what about those long-lived connections and high throughput workloads, the constant pain in our side again, right? So when you look at the more traditional proxy model you see with the PaaS, like in Kubernetes, there's some kind of service proxy in front, right? So to simplify it, right, the container is using the IP that's provided on the host, or the interface provided on the host. And then normally, whatever the PaaS is, even Mesos traditionally, right, will dynamically assign the port that that container binds to and then receives traffic, right? So most people get around that by having a service proxy in front of the system that lets you talk to that proxy on a standard port you would expect, and then route that back to the different containers that you have on whatever the dynamic port was they were assigned. So think about me having 40 instances of an application in a site that's processing 6 gigabits per second, right? Probably not going to make it through the service proxy without knocking it over. So that led us to kind of investigate some different networking models that we could use with Mesos, and we ended up landing on Project Calico. So it is a layer 3 virtual networking solution. It essentially installs a kernel module on each of the hosts that makes itself a BGP peer, and it advertises routes via BGP. So you can kind of think of it as, instead of your host getting an individual IP that all your containers share and use dynamic port binding, they actually get a true IP address per container, which is advertised on the network. So now your container is a true first-class citizen on your network. All your containers can actually route to each other and talk to each other if you allow them to do that. And you no longer have to worry about the dynamic port mapping or funneling that stuff through a proxy. You can let your app run on the standard ports that you would expect. So really we have a pool of addresses available for different workloads. Some are public, some are private. You can segment them out in different ways that you want to. As containers come up, we have a fork of both Mesos and Marathon that we used to implement this at first. I think the Mesos community is moving to add this to the Docker executor. We had to move a little bit faster than that, so we took a couple of shortcuts. So we have Mesos adding the IP to the container right after it starts up. At the time we were experimenting with this, we tried out Docker Lib Network. It wasn't quite stable enough for us to use. Had a few bugs with trying to add the networking interfaces, as well at the same time as we were trying to use it. Every new version that came out was changing the Lib Network interface. So we tend to run into that a lot in this space. You can also use Calico to define ACL definitions. So I can actually prove that I'm providing some network segmentation between my different services. So really how that works is a Calico daemon runs on every single one of the Mesos agents. And it checks back in with the Calico pool to see what addresses are assigned where and what application they belong to. And it essentially updates IP tables rules on the host at all times to allow communication to new containers that are added and remove ones that are no longer running under that IP address, and then be able to reclaim IPs that we're using. So this gets us to where things really get tricky with long-lived connections. Now I can assign an IP to my container, right, so that I get out of the service proxy business, right? So that I can let all that throughput run in and talk to that container. Still doesn't get me out of the business of draining those long-lived connections, right? I just solved the high throughput problem. So how do I deal with deploying apps that have long-lived connections? So what we ended up doing is using a local services load balancer and assigning public VIPs out in the space where our traffic comes in. We map those back to the host that we're talking to, and then we use NAT rules to map the traffic to the IP address of the container that's currently serving the request, right? So in your blue model, you have the public VIP, it's routing traffic, and the NAT rules are telling it to route to the IP address of this container. So then we get to the green part, right? So you have your dev or engineer here who's going to come and do their deployment. They're going to hit the deployment API, and it's going to deploy a new version of that application side by side next to the old one. And we can do this as many times as we want to. As soon as that application is deployed, we can flip a switch, and it begins to map traffic over to the IP address of the green container that was just deployed. So what that does is it routes all new incoming requests to the new version of the application while letting the old version continue to process the connections and uploads that it was receiving. And when those connections are done, it then allows that container is drained, and it can then be that task can then exit. And so, we can continue to keep versions adding and let the old containers continue to sit and drain. So this solved the problem of having a limited number of public IPs, but being able to deploy as many changes as we want to by using the NAT rules to go around that. So how did all this change the dynamics of our team that actually worked on it? I think we finally got to the true spirit of what DevOps is supposed to be. If you build it, you own it. The automation team kind of turned into the platform dev team. So they write the code that changes the configuration. They write the forks and patches to Mesos. They maintain the Calico networking tools. They maintain the Zookeeper. We still have a bunch of configuration management code that we actually use to deploy Mesos. There's no more throwing things over the wall. The app devs are on call for their applications. They're responsible for all the errors in their applications, and they're responsible for the monitoring and alerting on their applications. Right? The platform dev team is responsible for the monitoring and alerting on the Mesos and Marathon platform itself, and that platform is up and doing its job. Both teams now feel their own pain. They all have their own on-call rotations for the different services that they're responsible for. No more separate DevOps team that just does the automation. Right? So rather than taking ownership of a function in the stack, we started taking ownership of the different products that are in the stack. So that really enabled rapid development of new microservices on top of the platform. Maybe 6 months ago, I could tell you all the containers that used to run on Mesos at any given time, who all our users are. I definitely cannot name all the applications that are on there now. It really got feature development going like gangbusters. It enabled the devs to just get their app working in a Docker container, get the deployment running in our staging environment, and the next thing you know, they're delivering new features out into production. It's really easy to automate the deployment. We have a deployment tool that we use to talk to the Marathon REST APIs and deploy easily to it. And now all the config management is pushed down to the platform layer. So no more writing all that config management for each one of the applications. We do, however, have a significant investment still in orchestrating the platform layer itself. But I really think it improved our development culture overall, strong relationship between the app devs who are now the customers of platform engineering and are treated like so. And everybody's really taken strong ownership and responsibility of the things they're responsible for. Some of the challenges we still face, we have not solved the persistence problem. So running things like a relational database in Mesos, we haven't figured out how to do that yet. Normally that involves some sort of shared storage. We're not there with that yet. We are running apps that have some data persistence, like Kafka, and are beginning to experiment with some of the Cassandra frameworks. The only reason we're able to run those is because they have clustering at the application layer as well. So most of the frameworks that provide data persistence on their own basically have some sort of stickiness setting, right? So if I'm the Kafka framework, and I run 3 brokers, and I use data that's stored locally, if I just do an upgrade of that broker and restart it, or it exits because it, it got killed by OOM, then it'll try for a certain period of time that's configurable to restart that service on the same slave it was running on previously, so it can pick up its data directory, right? Only if that host doesn't actually return for scheduling does that broker then get scheduled somewhere else, and then Kafka recreates that data. And that's kind of how those services get away with that without providing any kind of shared storage. But for things like Postgres as a service or spin up MySQL on demand, we're not there yet. Similar to another Mesos talk we're exploring earlier, we actually are about to start exploring scale I/O both on our Mesos side and for our open stack infrastructure for block storage. Some of the other problems we have is that we've had to fork a lot of projects and maintain a lot of patches. Open source moves fast. People say we're like on the leading edge of technology. We call it the bleeding edge because it hurts, right? When we were trying to initially get this platform off the ground, we were on a timeline to be able to implement this. We had Mesos changing versions, implementing features we needed, but not being compatible necessarily with the Marathon version that was currently out, while at the same time experimenting with Docker Lib Network, who's changing its interface on us, right? So the stuff moves in these communities at the speed of light because they're so active right now. So it's definitely takes a lot of time to keep up with what versions of what work together and keeping up with patches that have to be made to keep the environment stable. Platform maintenance is still relatively difficult. There's a lot of gotchas to orchestrating upgrades and configuration changes to Mesos. There's some attribute settings you can do that'll tell a Mesos slave to dump all the workloads that it runs on it and reschedule them all. And while Mesos can recover from that, it's not necessarily the ideal behavior. Upgrading Docker is also still a bit of a hassle. Some of the guys on the team want to start exploring other container solutions like Rocket, mainly because of that Docker daemon. Upgrading Docker and restarting that daemon requires you to drop all the workloads on the host, right? So sometimes that's okay. Other times, when managing things like long-lived connections, not so much, because we still have to be able to drain those connections before we do that. So that becomes a significant pain for us to manage. Some of the keys, I think, to our success have been that we have a super awesome team. Everybody codes. We have an automate first attitude, and we're always continuously trying to improve the process. And I think I better save room for questions. I think it's 5 o'clock now.
So I think we have 5 minutes for questions, and we have one question.
Okay.
I think you answered already. Okay, what storage backend are you using for object storage? Ceph, Git, or Homey?
So I traditionally came from EMC Cloud Services. So EMC is the parent company of a bunch of companies like RSA, VMware, Pivotal, and now VirtuStream. So some of this object storage technology existed before we joined with VirtuStream. So it's all based on EMC storage products. And there's a mix in the environment of what those storage products are. But they're EMC storage products written specifically for object store, but then with us applying a bunch of application layer glue in front of it on this microservice platform to get it into the exabyte scale range.
Okay, I don't see any more comments. This question was asked by my listeners. Are you satisfied with the answer? Okay, any more questions?
Is there any other frameworks
Yeah, so we are running right now Marathon. We are running the Kafka framework. So with the Kafka framework, that also led us to the exhibitor framework. So Kafka requires Zookeeper to run. If you want to run the Kafka framework on top of your Mesos environment, really dumb to share the same Zookeeper, right? You're going to then allow users that can write in some weirdo pattern to your message bus that has the potential to be able to kill Zookeeper performance. that's affecting how you schedule and run all of your workloads. So luckily, we learned that in the lab and not in production. But that led us to look at the Zookeeper framework. And I'll get into a couple of changes that have come out with that that kind of came out of our use of that, right? So Exhibitor is an open source tool that I think is originally open sourced by Netflix for orchestrating changes to a Zookeeper cluster, right? So it was managing that on top of VM infrastructure, right? So that was turned into a Mesos framework, which gives you an API for deploying a Zookeeper cluster, just like the Kafka gives you an API that deploys Kafka programs. So both of those actually register with service discovery. So we have the framework that runs Kafka is configured to point at the service address of the Zookeeper servers, right? And then those register at service discovery, and the Mesos frameworks make sure that there's always the correct number of Zookeeper frameworks. We just battled through a few bugs in the Zookeeper framework, where you couldn't run more than one instance of Zookeeper on a particular bare metal host. So we actually pushed in the community, and one of our friends that helps us out a lot put in some changes for us to be able to Dockerize that and help us get past that segregation, because we were limited to running one Zookeeper per node, and we started ending up getting a lot of Kafka deployments going on in the wild. So Kafka became more popular than I ever imagined. We figured out how to run the framework and deploy it for one particular application. I think now we're running 5 or 6 different instances of the framework, being used by a bunch of different apps, and now it's going to support all our logging infrastructure to be able to centralize the application logging on that message bus before feeding it up to the log infrastructure. One of the other frameworks that's still R&Ding on is a DataStax Enterprise framework, and we're kind of exploring what moving Cassandra orchestrated by Salt on VMs would look like, being able to run that on Mesos and managing that. We have some pretty large Cassandra infrastructure going out, so it's become quite the headache to try to orchestrate changes in that. So we're looking for the ability to do that with a real program. One thing I don't think we have a good solution for yet that I'm hoping for is something better for scheduling jobs.
Okay, more than 10 answer. So I think that we are running out of time, so I will